Hey Chemistry, coming to you on a smoky day here in the Pacific Northwest. Today's lesson is cohesion, surface tension, and adhesion. Let's get started. So we're going to focus on how hydrogen bonding allows water molecules and other substances to maintain their cohesion, adhesion, and surface tension. We're going to define what those terms are and talk about why they're so critically important to how natural systems function. So it comes back to this idea of van der Waals forces, which are the sum of all of the attractive forces between molecules. We've gone over what those main forces are. We've talked about ion-ion, ion-dipole, dipole-dipole, dipole-induced dipole, and dispersion forces. Now let's see how these van der Waals forces interact to give certain substances their properties. So again, hydrogen bonding, as a summary, is the interaction between a hydrogen atom that is on a polar molecule and a highly electronegative atom from another molecule with strong dipole-dipole interactions. For instance, the oxygen of a water molecule being attracted to the hydrogen of another water molecule. Because of this strong dipole-dipole interaction, these molecules are attracted to each other with very strong forces. So strong, in fact, that they can overcome the forces of gravity in some cases to stick together. So take a look at this water droplet right here, and you'll notice that it's nearly spherical. The water molecules that are up here are being pulled down by the force of gravity, but they are being held up by what we call surface tension, which is the interaction that they have with all of the water molecules around them. And so here's surface tension in a water droplet over here, and you'll notice that this droplet here is this water molecule is being held by all of the water molecules around it, and they, in turn, are being held by all the water molecules around them. And these forces that are interacting between water molecules are helping to support each other against the force of gravity. We call that the surface tension, the ability to maintain the surface against forces of gravity. So surface tension allows you to do all sorts of interesting things. Like, for instance, you can take substances that are more dense than water that would have the tendency to sink through that water, and you can actually have them float on the surface because the water's surface tension is high enough that it can support that weight against the force of gravity without it sinking through. Now, once you dip that underneath the surface, it will sink through to the bottom. But as long as you don't disturb it too much, it's able to float on that surface. Water striders, in fact, take advantage of water's surface tension to allow them to sit on top of the water and to go across that surface without sinking in. So their feet have nonpolar surfaces that basically repel water or don't interact with the water molecules, and they're able to sit on top, and they're light enough that water can support their weight. So I have a video that goes into more detail about how water striders are able to stay on the surface of the water, so I'd like you to check that out in the Google Classroom. A lot of insects actually use the surface tension of water. A number of insects have a lot of hairs over the surface that actually maintain kind of a air layer between their actual skin and the water. And a lot of insects and spiders that live near rivers and ponds can actually walk over the surface of water or crawl across water without sinking in. All right, let's talk a little bit about why ice cubes float. I have a video also posted about this on the Google Classroom that you can check out that goes into more detail. But generally speaking, as substances get colder and the molecules slow down, they start to contract, they start to become more dense. As they're moving slower, they're not able to bounce off of each other with as much force and maintain that larger volume. So most substances, as they get colder, contract or become more dense. That's true of water, and that's true of most other substances. For instance, in the evening on a hot summer day, as the air temperature cools down, you'll often hear this creaking going on in your attic, in your ceiling, on your roof, and that's the particles that are cooling starting to contract. However, an interesting thing happens with ice. When water molecules begin to form that hexagonal crystalline structure and they begin to lock into place, they have to produce the right orientation so that all of the hydrogens line up with oxygens and all of the oxygens line up with hydrogens. And in doing so, it actually creates a crystalline structure that has a lower density or more space between the molecules than when they were a liquid kind of rolling all over each other. So ice cubes are one of the only substances on Earth, perhaps the universe, whose solid phase is less dense than its liquid phase. It's very rare, but it does have a lot of really important real-world implications that I want you to think about. What would happen to the Earth if ice didn't float? What would happen to the Earth if ice sank instead of float? It's pretty crazy. All right, so we'll continue on with this topic in the next set of videos, focusing on the concepts of cohesion and adhesion.